Welcome to the second part of this lesson where we talk about solving trigonometric equations that involve multiple angles. What do I mean by that? Well, prior to this lesson, you should have been working on problems, and I know this is a simple problem, but where they were single angles. What do I mean by single angles? If you look at the argument of the sine of x, this is single. It's a 1x. It's not a 2x, it's not a 4x, it's not a 1/2 x. It's a single, it's a 1x. So if you look at this graphically, we want to know if on the graph of the sine curve, where does it hit the y value of 1/2? So I'm going to use Desmos to kind of show you that here is the sine curve. I have it zoomed in. It's about 0 to 2 pi. Let's just look at that particular cycle or period of the graph. And we have a solution at pi over 6, and we have a solution at 5 pi over 6. The solution that you see on the right side of your screen would be beyond 2 pi. So those would be the specific solutions to that equation. If we wanted to talk about the general case, it would be pi over 6 plus 2 pi n, where n is a member of the integers, and 5 pi over 6 plus 2 pi over n, where it was a member of the integers, to talk about all of them. What we're going to change up today is we're going to make it multiple. So instead of looking at the sine of x, we're going to look at the sine of 2x. This argument is now a multiple angle. So 1/2 x, 3x, 1/4 x. We no longer have a single x. You have a period shift in your graph. So how does that affect your solutions? Well, let me click out of there. Let me go in and let me type in a 2. Because you have a period shift, you're going to have 2 cycles of the sine curve in that same space, right? So now if we look at specific solutions between 0 and 2 pi, we have a solution of pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. And then we would also have all of their coterminal angles if we're looking at a general solution. So notice how we got double the solutions. So with multiple angles, you're going to end up with a lot of multiple solutions. And some kids are like, well, are you always going to get 2 times, 3 times? It really does depend on the problem as to how many that you will get. So let's proceed with our first problem. We're going to talk about the secant of 4x. Let me scroll up. There we go. The secant of 4x equals 2. If I was approaching this as a test question, I would say to myself, is this a single angle equation to solve, or is this a multiple? And hopefully you notice by the 4x that this is a multiple. Can't stress this enough. If you're going to solve a multiple angle problem, you must find the general case first. And let's get through this first problem and you'll see why that's true. So here I guess, is the recipe, if you will, on how I go about solving these. The first thing I'm going to do is I'm going to use u substitution. I'm going to use the variable u. Why do we use u? It's arbitrary, but it is used a lot in calculus, so we might as well just kind of get used to using that variable at this point. So I'm going to let u equal 4x. In doing that, I get the secant of u is equal to 2. So now I kind of have this in a single equation angle format. Again, I'm going to be frank with you. I usually don't really think great in terms of cosecant, secants, and cotangents. I like things in terms of sine, cosine, and tangent. So I'm going to go ahead and I'm going to re-represent this as the cosine of u is equal to 1/2. I took its reciprocal. And I think better at that. Where do I have an x value that's at 1/2? Well, it's up here at pi over 3. And the other one is going to be down here at 5 pi over 3. I know that's not the clearest, but hopefully that just gives your mind going, and it should be a little bit clearer, hopefully, if you were able to print the notes or view them on your screen. All right, so again, this is a multiple angle. You have to do the general first. So I know that u is equal to pi over 3 plus 2 pi n. I also know that u is equal to 5 pi over 3 plus 2 pi n, where n is a member of the integers, and I'm probably not going to write that on every single problem. Save a little time and energy. But I don't want to know what u is. I am trying to solve for x. So this is where we know that u is equal to 4x, and now I'm going to put it back in for my u. So 4x is equal to pi over 3 plus 2 pi n, and 4x is equal to 5 pi over 3 plus 2 pi n. but I don't want to know what 4x is. I need to know what x is. So one way of thinking about this is you can certainly divide by 4, but instead I'm going to represent this as multiplying by its reciprocal of 1/4. I just think it's easier to do the fraction work by multiplying. So when I distribute 1/4 to 4x, I get x, which is what I'm trying to solve. If I take 1/4 times pi over 3, I multiply the numerators together, denominators together, I get pi over 12, and I don't need a calculator to figure that out. For some of you, pi over 3 over 4 might just be awkward. That's why I choose to write dividing by 4 as multiplying by a fourth. But if a student is going to make a mistake, it's right here. Remember, this is all the coterminal angles. We have a period shift. We're able to fit 4 secants in the normal 2 pi area then since this is a multiple angle problem. So your generator for adding coterminal angles isn't 2 pi over n. It's going to be pi over 2n. All right, so I'm going to do the same thing to the other factor. And I get x is equal to 5 pi over 12 plus pi over 2n. If the directions ask you for a general solution, you are now done. This represents all the possible solutions to this equation. However, if you have been asked to find the specific angles between 0 and 2 pi, it's going to look like this. So if you look in the book, obviously n means integer multiples, and you can put n equals 0 and n equals 1 and n equals 2 and crank out all of the arithmetic. This is how I've been teaching it, and kids are like, oh, I think that's a lot simpler and a lot more efficient. Pi over 12 is when n equals 0. You don't, that should be fine. But really, you just need to keep adding pi over 2 to the previous angle to get more coterminal angles. So just go ahead and convert pi over 12 into 12ths. So that's going to be 6 pi over 12. If I add it to pi over 12, that gives me 7 pi over 12. If I add another 6 pi, it's 13 pi over 12. If I add another 6, I get 19 pi over 12. And if I add another 6, I would get 25 pi over 12, and it is not necessary to write that because it exceeds 2 pi. It exceeds my interval. 24 pi over 12 is equivalent to 2 pi, so I don't have to go past that. So you got 4 solutions just from that one factor. You still have to do this factor. So now let's get all of the solutions from this factor. What's nice is you've already converted pi over 2 into 12ths. It's 6 pi over 12. So I get 5 pi over 12. When I add 6 pi to it, I get 11 pi over 12. When I get 6 more, I get 17 pi over 12. And then when I add 6 more, I get 23 pi over 12. And those right here, all 8, are the specific solutions between 0 and 2 pi. So on this problem, I'm going to go ahead and verify on Desmos. All right, we had a problem that was the secant of 4x. And we want to know where that is equal to 2. So let's see if we're correct. Trying to zoom in here properly. I need a little bit more room. There we go. So there we go. There's pi over 12. There's our 7 pi over 12 when we add 6 pi over 12 to it, 13 pi, and 19 pi. So those are the solutions from that first factor. And then in the second factor, we have 5 pi over 12, 11 pi, 17, and 23 pi all over 12. Okay, welcome to example 7. This problem is a little bit different than the previous because I have included a power in this problem. So I'm still going to start by asking myself, is this a single angle problem or is this a multiple angle problem? It's multiple. So these are the problems where we're going to use some U substitution, and we're going to go ahead and make sure that we do our general solution first. So I'm going to let U be 3x. So now I get the tangent squared of u is equal to 3, and now I can approach this like you did in part 1 where it's a single angle problem. But in order to solve, you're going to have to take a square root of both sides. And again, if a student is going to slide into the vortex and make a mistake, it's right now. the tangent of u is equal to plus or minus root 3, not just the positive principal root. So what happens is we know that the tangent is root 3 at the pi over 3 family, and because it's plus or minus, we're looking at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Now, I'm going to show you a little bit of a tip regarding our work. Don't write this down. Wait, and I'll tell you when you can start writing. It is mathematically correct to say that u is equal to pi over 3 plus 2 pi n, and 2 pi over 3 plus 2 pi n, and 4 pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. All legitimate, but that's 4 factors. We can be more efficient and cut this down into 2 by doing the following. Notice that pi over 3 and 4 pi over 3, they differ by pi radians. So I can cover these 2 statements by instead writing my general solution as u is equal to pi over 3 plus pi n. Furthermore, if you look at 2 pi over 3, let's go do a different highlighting color. If I look at 2 pi over 3 and 5 pi over 3, they also differ by pi radians. So I can rewrite those 2 statements in a little bit more efficient as 2 pi over 3, not plus 2 pi n, but pi n, and now you have taken care of those 4 statements, and you only have to do some work on 2 factors instead of 4. All right, so now, just like we did in the previous problem, we know that u is equal to 3x, and so we're going to go back and substitute that value back in for u. Next, we're not concerned about what 3x equals. We want to know what x equals. So you can divide everything through by 3 or multiply by 1/3. And that's going to give us x equals pi over 9. Do not forget to distribute to your generator to make more angles, and you get pi over 3n. And on this, I would get x is equal to 2 pi over 9 plus pi over 3n. If the directions ask you for the general solution, you are finished. However, if the directions want the specific angles between 0 and 2 pi, and friends, we're going to keep that in the directions pretty standard. All right, here's what I do. Pi over 3 in terms of ninths is 3 pi over 9. So start with pi over 9 and keep adding 3 pi in the numerator to the previous. So that's going to give me 4 pi over 9. Add another 3 to get 7 pi over 9. Add another 3 to get 10 pi over 9. And you're like, how far do I have to go? Well, 18 pi over 9 is 2 pi, so you have to keep going until you exceed 18. So let's go. We've got 13 pi over 9. And if I add 3 pi to 13 pi over 9, I get 16 pi over 9. And if I add 3 more, I would get 19 pi over 9, which exceeds 18 pi over 9. So I get 6 solutions from just that factor. So now I have to do the exact same for the second factor. 2 pi over 9. We've already converted into ninths. I keep adding 3 pi over 9. So I would have 5 pi over 9, 8 pi over 9. Learn to write NOP. 11 pi over 9. 3 more is 14 pi over 9. 3 more is 17 pi over 9. And those are our 12 solutions between 0 and 2 pi. So to show you again on Desmos, I've already pre-typed it in for you. And this is kind of a hot mess, but there is pi over 9, 4 pi over 9, 7 pi over 9, 10 pi over 9, 13 pi over 9, and 16 pi over 9. We got all of those from the first factor. And then I get 2 pi over 9, 5 pi, 8 pi, 11 pi, 14 pi, and 17 pi over 9 from the back two. Welcome to example 8. My rationale for doing this problem for you is because this is going to be a problem that combines a multiple angle with a problem that has a single angle. So when I'm looking at this has been pre-factored for you, so you can use the zero product property, and I can set the cosine of 2x equal to 0 and 2 cosine of x plus 1 equals 0. The factor on the left, this is a multiple angle, so we're going to use u substitution, where u is equal to 2x, so the cosine of u is equal to 0. Well, where does that occur on our unit circle? At pi over 2 and at 3 pi over 2. So it is mathematically correct to write this as pi over 2 plus 2 pi n and 3 pi over 2 plus 2 pi n if I want to refer to the general solution. But since these differ by pi, I can be way more efficient, and I can write that u is equal to pi over 2 plus pi n. But we don't want to know what u is equal to. We want to know what x is equal to. So let's go ahead and put 2x back in. And in order to get x by itself, we're going to divide by 2, which is the same as multiplying by 1/2. So I get that x is equal to pi over 4 plus pi over 2n. So far, this is a piece of my general solution. Let's talk about the 2 cosine x plus 1 equals 0. I'm going to subtract 1 from both sides and divide by 2 so that we end up with that cosine of x is equal to negative 1/2. We know that cosine, let's erase some of this. We know that cosine is negative in the second and the third quadrants. So where do you have x is negative 1/2? You have that at 2 pi over 3 and at 4 pi over 3. Unfortunately, the distance between those two is not pi, so there is no way to write them efficiently. So let me write this in yellow ink. If I wanted to talk about my general solution, I would have to write it as 2 pi over 3 plus 2 pi n, and I would have to write the last one separately as x equals 5 pi over 3 plus 2 pi n. So this would be your general solution if the directions asked for general. If the question asked for a specific solutions that were between 0 and 2 pi, we have to go to every factor. So let's take this factor. I would have pi over 4, and if I convert pi over 2 to fourths, that's going to be 2 pi over 4. So I get 3 pi over 4, add another 2 pi, I get 5 pi over 4, add another 2 pi, I get a 7 pi over 4, add another 2 pi, I get 9 pi over 4. That exceeds 8 pi over 4, which is 2 pi. So those are my specific solutions between 0 and 2 pi. All right, next, think about this, guys. 2 pi over 3 plus 2 pi n came from a single angle. So if you take 2 pi over 3 and you add 2 pi over it, you're going to exceed that interval. So you just get 2 pi over 3. And the same thing from this factor. This did not come from a multiple angle. You aren't going to generate a lot of answers. You're just going to get 5 pi over 3 because if you add 2 pi to it, we've exceeded. This is my specific solution, and let's verify on Desmos. All right, so there's my pi over 4. There's my 2 pi over 3, 3 pi over 4, 5 pi over 4, 4 pi over 3, and 7 pi over 4. And here's our last example. It is a word problem. I think it's actually pretty fun to do. A weight is oscillating on the end of a spring. You can see the picture, and the position of the weight relative to the point of equilibrium is given by the following equation, where y is the displacement in meters and t is time. So I just find this to be a pretty interesting problem, and here is why. They want you to find the times when the weight is at the point of equilibrium. So it's where y equals 0. So we're going to set this equation equal to 0 and solve. But sometimes kids ask, well, what do I do here? Well, let's multiply both sides by 12 and we can just get that out of there. So we get 0 is equal to the cosine of 8t minus 3 sine of 8t. And normally we tell you don't divide by a trig function because you could lose solutions. but sometimes you can transform into a different trig function by dividing. And that's what we're going to do here. I'm going to go ahead and bring the 3 sine t to the other side just so we make everything positive. So I have 3 sine 8t is equal to the cosine of 8t. So I now am going to divide both sides by the cosine of 8t. And if you're wondering, why would you do that? Because I'm not going to lose solutions. You can use your quotient identities and rewrite that as 3 tangent 8t equals 1. So now the tangent of 8t is equal to 1/3. And we are just going to treat this like any other multiple angle problem. The difference is we are going to have to use our calculator in order to solve. If I let u be 8t, then the tangent of u is equal to 1/3. This is not on the unit circle. So in order to solve, I'm going to have to take an inverse tan of both sides. So I've already done that in my calculator for you on Desmos to save a little time. The inverse tangent of 1/3 is approximately 0.32 radians. So u is equal to 0.32 radians, but friends, this is a multiple angle problem. And you have to think about what they just gave you, 0.32 radians is going to be in the first quadrant. Isn't tangent also positive in the third quadrant? What is that distance between those going to be? Pi. So all of the pi n revolutions are also going to work. We do not want what u is, we want what t is. So 8t is equal to 0.32 plus pi n. We're going to multiply by 1/8. That is going to give us, I've already used green, let's use hot pink. We're going to get t is equal to 0.32 over 8 plus pi over 8n. Think about it, 32 divided by 8 is 4, so move the decimal place over. So we have 0.04 plus pi over 8n. And in the problem wanted us to solve from where time was 0 to 1 second. So what does that mean? All right, well, we know that one of our solutions is going to be 0.04. Then we know the next solution is going to be 0.04 plus pi divided by 8, and that gives us 0.43. So now I'm going to take the previous answer of 0.43, and we're going to add pi divided by 8 to it, and we get 0.82. And if I take 0.82 and I add pi divided by 8, I get 1.21, and I've exceeded. So my solutions in terms of times that we would hit equilibrium between 0 and 1 second would be at 0.04 seconds, and then we would have 0.43 seconds, and then at approximately 0.82 seconds. Enjoy your rest of your web assign. There are 11 problems 18 to 28.